What if the brightest visitor in our skies isn't just another frozen wanderer, but a messenger? 3I-ATLAS is no ordinary comet. Its path, its timing, and its shimmering flyby past Mars have left behind anomalies we can't easily explain. Instruments picked up faint ripples in the dust, whispers of debris that look less like chaos and more like intention. Could this be a seed of life cast across the stars? Or a weapon disguised as ice? The deeper we dig, the stranger it becomes. Tonight we unravel the evidence, the rumours, and the terrifyingly plausible. Because if 3I-ATLAS isn't random, then neither is our future. And the question hangs heavy. If the rumours are true, how long do we really have? Stay until the end, because what you'll discover isn't just about the comet, it's about us, and what may already be in motion. Part 1. Latest twist. Something crossed the orbit of Mars on October 3rd, 2025, and millions of people are convinced we're being lied to about what it was. The object in question is officially called 3I-ATLAS, the third confirmed interstellar visitor to our solar system. It came from somewhere beyond the stars, somewhere that took it millions or billions of years to leave behind, and now it's racing toward the sun at speeds that would vaporize any spacecraft humans have ever built. The mainstream scientific community says it's a comet, probably just ice and rock wearing a dusty coat, following the same physics that govern every other frozen wanderer in the cosmos. They say the strange readings are instrumental artifacts, tricks of light and sensor noise. They say we're seeing what we want to see. But then the images leaked. On October 5th, 2025, a grainy sequence appeared on social media, allegedly captured by the Perseverance rover on Mars during the flyby window. The footage shows a dim streak moving against the star field, nothing unusual for telescope imagery, except for one thing. The streak has structure, multiple parallel lines, almost geometric, moving in perfect tandem. Within 6 hours, the post had 17 million views. Within 12 hours, NASA issued a statement calling it a processing artifact, a glitch in the image compression algorithm that creates false patterns in noisy data. Within 24 hours, 3 more alleged frames appeared from different sources, each showing similar geometrical patterns. The internet did what the internet does best. It lost its mind. Amateur astronomers started pulling every available data point they could access. Astrophotography forums exploded with analysis threads. Someone ran the images through pattern recognition software designed for satellite tracking. The software flagged anomalies. Not proof of anything, but enough to keep the fire burning. Enough to make you wonder why NASA felt the need to respond so quickly, so defensively, if it was really just noise in the system. Here's what we know for certain. 3I-ATLAS was discovered in November 2023 by the Asteroid Terrestrial Impact Last Alert System in Hawaii, the same network that gives us early warning for potential Earth impactors. At first, astronomers thought it was just another long-period comet from our own Oort cloud, the vast sphere of icy debris that surrounds our solar system, like a cosmic snow globe. But as observations accumulated, the trajectory became clear. This thing wasn't born here. Its orbital velocity was too high, its path too hyperbolic. It came from interstellar space, making it only the third confirmed object of its kind after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. But 3I-ATLAS is different from its predecessors in ways that matter. Oumuamua was tiny, maybe a few hundred meters, long, tumbling through space like a cosmic cigar or possibly a pancake, depending on which model you trust. It showed unexplained acceleration as it left the solar system, a tiny push that couldn't be fully explained by outgassing. The normal process where frozen material on a comet's surface turns to gas and creates thrust. Scientists proposed a dozen natural explanations, from hydrogen ice to cosmic dust pressure, but none fit perfectly. Then it vanished into the darkness beyond Neptune before we could study it properly, leaving behind more questions than answers. 2I/Borisov was more cooperative, a well-behaved interstellar comet that looked and acted almost exactly like comets from our own solar system. It had a proper coma, the fuzzy cloud of gas and dust surrounding the nucleus. It had a tail pointing away from the sun, exactly as expected. It followed the rules. Scientists breathed a sigh of relief. The universe made sense again. Now comes 3I-ATLAS, and the rules seem to be bending. The rumours started quietly. whispers in academic circles that something about the trajectory wasn't quite right. Observers noted the object seemed to be maintaining stability better than expected given its size and composition estimates. Some claimed the velocity showed minute variations inconsistent with pure gravitational flight. These variations were tiny, well within error margins, but they were there. Or maybe they weren't. Error bars are wide enough to hide a multitude of interpretations, which is exactly what makes this moment so combustible. Then came the mass estimates, and things got complicated. Early calculations suggested 3I-ATLAS might be significantly more massive than initially projected, possibly orders of magnitude heavier than Oumuamua. If true, that changes everything. A heavier object requires more force to alter its trajectory, which means any anomalies in its path become harder to explain through natural processes alone. It also means impact scenarios become exponentially more catastrophic, though the current trajectory shows no Earth-crossing potential. At least, not yet. The Mars flyby was supposed to settle some of these questions. At closest approach, 3I-ATLAS passed within approximately 5 million kilometres of the red planet, close enough for multiple orbital missions to observe it with unprecedented resolution. Mars Express, the European Space Agency's veteran orbiter, trace gas orbiter with its advanced spectrometers. NASA's MAVEN mission studying the Martian atmosphere, the Mars Reconnaissance Orbiter with its powerful high-rise camera, even Perseverance down on the surface, pointing its cameras skyward. Every major instrument in the Martian system had eyes on the object. And then we waited for the data. That's where the conspiracy theories found oxygen. In the age of instant information, any delay feels suspicious. People forget that deep space data transmission works at the speed of light, which sounds fast until you remember Mars is currently about 200 million kilometers away, meaning signals take roughly 11 minutes to cross the gap. Add in compression time, processing time, calibration checks, and the fact that orbital missions weren't designed for rapid response astrophotography, and delays become inevitable. But inevitability doesn't stop speculation. The leaked images appeared before any official release, which should have been the first red flag. Real scientific data goes through verification protocols before publication, precisely to avoid spreading false positives. But in the court of public opinion, official channels move too slowly. The leaked frames, authentic or fabricated, filled a vacuum that institutions were too careful to occupy. NASA's denial was swift and technical, citing known artifacts from JPEG compression, cosmic ray hits on camera sensors, and hot pixels that can mimic structural features in low-light imagery, all of which is absolutely true, all of which happens regularly, all of which provides perfect cover if you're trying to hide something real. But if the rumours are true, how long do we have? That depends entirely on what 3I-ATLAS actually is, and what it's here to do. The survival timeline shifts dramatically, depending on whether we're looking at a natural comet or something with intent. A comet will fly past, maybe give us a spectacular show in the night sky, and disappear back into the darkness. A probe might do the same, a reconnaissance mission gathering data for some distant civilization, or it might have other plans entirely. The clock is already running. Perihelion approaches. The sun waits. We're about to find out if this was just noise in the system, or the first real signal. Part 2. Break and bait. Mass matters. The mass of an object tells you how seriously to take it, and recent analyses suggest we may have seriously underestimated 3I-ATLAS from the very beginning. Initial estimates placed the object somewhere in the range of typical long-period comets, maybe a few kilometers across, weighing billions of tons but nothing extraordinary by cosmic standards. These calculations relied on brightness measurements, combined with assumed albedo values, the reflectivity of the surface. You're essentially trying to determine the dimensions of a charcoal briquette in a dark room, using only a flashlight beam reflected back at you. But as 3I-ATLAS approached and more telescopes locked onto its trajectory, something in the calculations started to shift. The object was brighter than expected at certain wavelengths, dimmer at others. When researchers ran the updated data through refined models, the mass estimates climbed. Some now suggest 3I-ATLAS could be 10 times more massive than Oumuamua, possibly more. That changes the entire conversation. A massive object showing any kind of trajectory anomaly becomes exponentially harder to explain through natural outgassing alone. The amount of gas you'd need to vent to alter the course of a truly massive body approaches absurdity. Let's put this in perspective. Oumuamua was estimated at roughly 100 metres long and 400,000 tonnes in mass. At that size, the unexplained acceleration it exhibited could theoretically be produced by outgassing hydrogen ice. The math was uncomfortable but possible. Now scale up to 3I-ATLAS. If current estimates are correct and we're looking at something in the range of tens of billions of tonnes, the outgassing required to produce even minor trajectory adjustments becomes staggering. You'd need to vent material at rates visible to every telescope pointed in that direction. The coma should be enormous, the tail spectacular. Some of that is happening. 3I-ATLAS has developed a coma and tail? Absolutely. But the relationship between observed outgassing and trajectory stability seems off, like watching a cargo ship make tight harbour manoeuvres with no visible tugboats in sight. The math doesn't quite close the loop. Density becomes the critical question. What is 3I-ATLAS actually made of? A loose rubble pile would have relatively low density, maybe twice that of water, consistent with typical comet nuclei. But if this thing is packing mass into a smaller volume than cometary material should allow, then we're talking about something fundamentally different in composition. Metal has been suggested. Not pure metal, but a core of metallic material wrapped in an icy shell. Think of it as cosmic armour, a protective layer that allows dense internal structure to survive the journey through interstellar space. Natural metal-rich asteroids exist, remnants of shattered planetesimals. An interstellar asteroid wouldn't be impossible. But an interstellar asteroid wrapped in a cometary disguise starts to sound less like astronomy and more like engineering. Speculative voices online have latched onto the idea of an engineered shell, a deliberately constructed outer layer designed to mimic a natural comet while protecting internal payloads during a journey measured in millions of years. Scientists have proposed similar designs for human interstellar probes, using ice shields to protect delicate instruments from cosmic rays and interstellar hydrogen atoms that become deadly projectiles at relativistic speeds. The term mobile asteroid ship has entered the vocabulary, combining the protective mass of an asteroid with the deliberate trajectory of a spacecraft. In this model, 3I-ATLAS was built, or at least modified, using a captured comet nucleus as raw material. The ice provides reaction mass for extremely long-duration propulsion. The rocky components provide structure and radiation shielding. The trajectory data supports unusual stability. An object moving through space experiences tiny but cumulative forces from solar radiation pressure, gravitational perturbations, even drag from the thin interstellar medium. Over millions of years, these forces should randomize trajectories, making precision targeting essentially impossible unless course corrections occur. 3I-ATLAS arrived on a trajectory that will take it past Mars, then past the Sun, then back out into interstellar space. The precision isn't perfect, but it's better than random chance would suggest. Either it got extremely lucky, or someone aimed it. Error bars create narrative wiggle room, which is why this remains speculation rather than science. But if we take the high-end mass estimates seriously, if this thing really is billions of tons, somehow maintaining stable flight through interstellar space, then the thrusters required to make even minor adjustments become enormous. We're talking about propulsion systems capable of moving mountains, even if they're only making tiny tweaks spread out over millions of years. Which raises the question, where does that energy come from? Solar panels wouldn't work during the interstellar cruise phase where starlight drops to essentially nothing. Nuclear fuel has limited lifespan measured in thousands to millions of years, unless the power source is the sun itself, waiting ahead like a cosmic gas station. This is where timing becomes suspicious. 3I-ATLAS is approaching perihelion, the moment of closest solar approach, when radiation intensity peaks and available energy reaches maximum. If you were designing an interstellar probe that needed to conserve power during a million-year journey, you'd want to reach your destination in a low-power dormant state, then use solar energy to reactivate systems. You'd time your arrival to maximize solar exposure while minimizing risk from heat and radiation. Perihelion is exactly that moment. If mass tips the scale toward artifact, then activity patterns tip the suspicion even further. A massive object should behave predictably under known forces. If it doesn't, if there are anomalies that can't be explained by outgassing or modelling errors, then we're left with uncomfortable alternatives. Either our understanding of physics is incomplete in ways that happen to make natural objects look artificial, or we're looking at something that actually is artificial and trying to pretend it's natural. The numbers tell part of the story. Billions of tons moving through space with unexplained precision, showing composition anomalies, developing activity patterns that don't quite match expectations. What tips speculation into obsession is when the instrument starts seeing things that shouldn't be there. That's where Mars comes in, and why those leaked images matter more than they should. If 3I-ATLAS is just a comet, Mars should have seen a comet. If it's something else, Mars should have seen something else. And if Mars saw something else but we're being told it saw a comet, then the real question isn't what 3I-ATLAS is. The real question is what someone doesn't want us to know. Part 3. Mars. Encounter. Who saw what? October 3rd, 2025 was supposed to be a routine observation opportunity, the kind of coordinated campaign that happens whenever something interesting passes through the inner solar system. Instead, it's become a focal point for every conspiracy theory about institutional cover-ups and hidden truths. The Mars flyby itself was straightforward in astronomical terms. 3I-ATLAS passed within approximately 5 million kilometres of the red planet at closest approach, near enough for high-resolution observation, but far enough to pose zero collision risk. Every functioning orbital mission received targeting coordinates weeks in advance and allocated observation windows accordingly. Mars Express pointed its high-resolution stereo camera at the sky during flyby windows. The trace gas orbiter captured spectra looking for emission and absorption lines that reveal chemical composition. NASA's MAVEN mission performed basic photometry, measuring brightness changes over time. The Mars Reconnaissance Orbiter's high-rise camera, one of the most powerful cameras outside Earth orbit, should have caught anything unusual happening during flyby. Down on the surface, Perseverance rover's cameras pointed skyward during predicted windows. In total, roughly a dozen instruments across multiple missions had eyes on 3I-ATLAS during the Mars encounter. Together, they represented humanity's best chance to observe the object from close range using assets already in place. Then we waited for the data to come down. This is where misunderstanding turns into suspicion. Deep space communications work on physics timelines, not internet timelines. Earth and Mars are currently about 200 million kilometres apart, meaning light-speed signals take roughly 11 minutes one way. That's an inherent delay that no amount of engineering can eliminate. Add in data compression time. High-resolution images are enormous files by spacecraft standards, requiring hours to transmit. Add in calibration requirements. Raw spacecraft data arrives with instrumental signatures, noise patterns, and distortions that must be corrected before images become scientifically useful. Add in coordination protocols between multiple space agencies, each with their own data release policies. All of which means the normal delay between observation and public release can stretch to days or even weeks for complex measurements. To someone accustomed to smartphone photography where every image is instantly shareable, this feels like stonewalling, but it's just physics and bureaucracy moving at their normal glacial pace, optimized for accuracy rather than speed. Unless, of course, someone decided to slow things down even further. The leaked images appeared on October 5th, 2025, 2 days after flyby. They're allegedly sourced from Perseverance's raw image archive. The frames show a dim streak, moving against background stars, which matches expectations for a distant object crossing the field of view. But embedded in that streak are parallel lines, almost like ruled marks on a measuring stick, spaced too evenly to look random. NASA's response blamed compression artifacts, specifically JPEG block boundaries that can create artificial straight edges in images. This is absolutely a real phenomenon. The problem with this explanation is that the alleged Perseverance images don't use JPEG compression. They're stored as PNG files, which use lossless compression that shouldn't introduce block artifacts. When this discrepancy was pointed out, the official explanation shifted to hot pixels, individual detector elements that give spurious readings. Hot pixels are real, but they typically appear as dots, not parallel lines. You'd need multiple hot pixels lined up perfectly to create the pattern seen in the leaked images, which seems unlikely but not impossible. The third explanation blamed cosmic rays, high-energy particles from space that strike camera sensors and create bright streaks. Cosmic rays definitely cause streaks, but they're random, creating streaks at all angles. The parallel alignment seen in the leaked frames would require multiple cosmic ray strikes at nearly identical angles within a single exposure, stretching coincidence without breaking it entirely. Each individual explanation is plausible. Combined together, they suggest a pattern of retrofitting explanations to match observations rather than predicting what should appear. This is what fuels conspiracy thinking. When authorities offer multiple shifting explanations for the same phenomenon, it looks like searching for the story that sticks rather than reporting the truth. Amateur analysts jumped on the inconsistencies. Multiple forums dissected the leaked frames pixel by pixel. Some claim to find additional structure beyond the initial parallel lines, geometric shapes that natural compression artifacts shouldn't produce. Others found nothing, seeing only noise that human pattern recognition systems interpret as meaningful. The debate quickly became tribal, splitting into camps convinced they were seeing proof of artificial structure versus camps convinced they were watching mass delusion in real time. Neither side could prove their case definitively, because neither side had access to the original, unprocessed sensor data, only the degraded copies circulating online. Meanwhile, the official processed images from Mars missions remained unreleased. Days passed. Then a week. ESA updated its Mars Express data archive with observations from early October, but the specific frames from October 3rd showing 3I-ATLAS weren't included. NASA's archive showed gaps during the predicted flyby windows, which could mean observations weren't successful, data hadn't finished processing, or files were being held for scientific publication first, or something else entirely. The silence created a vacuum that speculation filled instantly. Why no images if everything was routine? The most boring answer is that successful observations require more processing time before release, while unsuccessful observations might not be worth publishing at all. If tracking failed or instruments didn't capture usable data, there's no conspiracy, just operational reality. But boring answers don't explain why preliminary results aren't announced. A simple statement like, observations were successful, processing continues, expect data release in 2 weeks, would deflate most conspiracy theories instantly. Instead, we get silence, which feeds the narrative that something unexpected happened and someone's deciding how to handle it. The most troubling possibility isn't that something genuinely anomalous appeared in Mars imagery. It's that multiple instruments saw the same anomaly independently, creating a pattern too consistent to dismiss as instrumental error, but too ambiguous to confirm as artificial structure. If Mars Express, Trace Gas Orbiter, and Mars Reconnaissance Orbiter all captured similar geometric patterns during flyby, then we're no longer talking about camera glitches. We're talking about something real that multiple independent sensors detected, that something could still be natural. Comets can develop jets of outgassing material that create plume-like structures. Dust entrained in these jets might produce linear features under the right lighting conditions. Fragment clouds from recent breakup events might appear as parallel tracks. There are natural explanations that could create geometric appearance without invoking artificial origins. But those explanations should be testable against the actual data, which brings us back to the problem of data availability. When data stays locked behind institutional walls, even for legitimate reasons, it creates the appearance of gatekeeping. And in today's environment, appearance often matters more than reality. The history of governmental response to potential extraterrestrial contact isn't encouraging. During the Oumuamua encounter, it later emerged that Department of Defense tracking assets monitored the object continuously, producing high-resolution trajectory data that remained classified for months. The eventual public release showed nothing particularly suspicious, but the secrecy itself suggested authorities were at least considering non-natural explanations. If similar protocols engaged for 3I-ATLAS, we wouldn't know until long after the fact, if ever. The existence of classified observations doesn't prove a cover-up, just operational security around sensitive monitoring capabilities. But operational security and truth suppression look identical from the outside. We're left with a situation where multiple instruments observed 3I-ATLAS during Mars flyby. Data transmission occurred according to normal protocols. Processing continues according to standard timelines. And yet, somehow the vacuum of official imagery has become the story itself. The speculation has already escaped containment. What if Mars's first contact with an interstellar visitor wasn't just a scientific opportunity, but an intelligence-gathering operation by something that knows exactly how to avoid triggering obvious alarms? What if the geometric patterns represent deliberate signalling? What if the delay isn't about processing time, but about institutional debates concerning disclosure and what the public deserves to know? Or what if it's all just noise, compression artifacts and hot pixels and cosmic rays creating phantom patterns, while the real 3I-ATLAS flies past completely mundane and we're chasing ghosts made of wishful thinking? The truth is probably in that data, waiting to be released, ordinary or extraordinary depending on what the cameras actually caught. Until then, we're spectators watching a cosmic theatre where the curtain hasn't risen yet, and every delay makes us more certain something's wrong. The question isn't whether Mars saw something during the 3I-ATLAS flyby. We know Mars saw something. The question is whether what Mars saw matches what we've been told to expect, or whether the universe just got more complicated than anyone was ready to admit. Part 4. Coma, Tale and Strange Chemistry. Telescopes around the world and in orbit have been dissecting 3I-ATLAS with spectroscopy, the technique of splitting light into its component wavelengths to reveal chemical composition. What they're finding doesn't quite add up to a typical comet signature, and that's causing quiet concern in astronomical circles even as official statements maintain confident normalcy. The James Webb Space Telescope turned its infrared eye toward 3I-ATLAS in late September 2025, capturing spectra during multiple observation windows. The preliminary results showed strong carbon dioxide emissions, exactly as expected when frozen CO2 sublimates directly from ice to gas under solar heating. But the ratios were off. The carbon dioxide signal was stronger than models predicted for an object at 3I-ATLAS's distance from the Sun. At roughly 2 astronomical units out, comets typically show water vapour as the dominant outgassing species, with CO2 playing a secondary role. Here, the carbon dioxide seemed to be doing most of the heavy lifting, dominating the spectral signature in ways that suggest either unusual composition or unusual heating patterns. One explanation involves subsurface reservoirs of pure CO2 ice that could survive closer to the Sun than more volatile water ice, then vent explosively once exposed to solar radiation. Perhaps 3I-ATLAS formed in an unusually cold or carbon-rich environment, giving it composition statistics at the extreme end of the normal distribution. Or perhaps the carbon dioxide isn't coming from ice sublimation at all, but from chemical reactions involving surface materials exposed to solar radiation and cosmic rays. This would explain the stronger than expected signal without requiring exotic composition, but it would also suggest surface chemistry, unlike anything we've seen in solar system comets. Then there's the colour. Ground-based observers noticed something strange in late September 2025. The coma around 3I-ATLAS showed a distinct green tint, visible even in amateur telescope images as a subtle emerald glow surrounding the central nucleus. Green comets aren't unheard of. The colour typically comes from diatomic carbon, molecular fragments created when sunlight breaks apart larger carbon compounds in the coma. Except the green from 3I-ATLAS seemed too intense for the object's brightness and distance. Some spectra also hinted at cyanogen, another carbon-nitrogen compound that contributes to green coloration. The presence of cyanogen at detectable levels raised questions about nitrogen content. Where did the nitrogen come from? Comets do contain nitrogen compounds frozen into their ices, but usually in trace amounts. 3I-ATLAS seemed to be venting nitrogen-bearing molecules at higher rates than typical comets manage. Nitrogen chemistry matters because it connects to potential biological or prebiotic processes. Amino acids require nitrogen. Nucleotides incorporate nitrogen atoms in their structures. A nitrogen-rich comet arriving from interstellar space could theoretically carry complex organic molecules, possibly even the chemical precursors necessary for life to emerge on suitable worlds. Or it could be carrying something that already made that transition from chemistry to biology, preserved in frozen stasis for the journey. The really strange chemistry showed up in trace metal detections. Multiple observation teams reported spectral lines corresponding to nickel atoms in the coma. Nickel emissions have been detected in solar system comets before, so the presence of nickel isn't immediately alarming. But the abundance seemed wrong. For 3I-ATLAS, the nickel signature appeared stronger than iron, which is the opposite of what you'd expect based on cosmic abundance patterns, where iron typically outnumbers nickel by more than 10 to 1. Several explanations have been proposed. Maybe the nickel is concentrated in surface materials that ablate preferentially during the early stages of activity. Maybe the iron is present but not excited to the same emission lines. making it less visible despite being more abundant. Or maybe 3I-ATLAS contains genuinely anomalous metal abundances that reflect formation conditions radically different from anything in our solar system. Nickel-iron alloys form the cores of differentiated bodies, planetesimals large enough to melt internally so that heavy metals sink toward the centre. When these bodies shatter through collisions, fragments from the metallic core become metal-rich asteroids. A chunk of a shattered core travelling through interstellar space would definitely show unusual metal signatures. But cores don't have ice. They're solid metal and sulfides, not the volatile rich material that creates cometary activity. For 3I-ATLAS to show both high metal content and significant outgassing activity, you'd need some kind of hybrid structure, a metallic core wrapped in an icy mantle. That's theoretically possible as a collision product. Or it's possible as an engineered structure, metal framework wrapped in ice shielding for the long journey between stars. The tail adds another layer of mystery. 3I-ATLAS has developed both types of tail as expected, broad and diffuse with the characteristic fan shape of escaping dust. But in some images from late September, observers noted the ion tail seemed to show slight deviations from perfect anti-solar alignment, bending or kinking at angles that didn't match expected solar wind conditions. Ion tails are sensitive indicators of local space weather conditions, responding to changes in solar wind speed, density, and magnetic field strength. What looked anomalous might just be 3I-ATLAS responding to solar wind structures we hadn't measured directly during the observation windows. But some researchers noted the tail geometry seemed wrong, even accounting for known solar wind variations. The bends appeared in the wrong direction for standard pressure effects, almost as if material was being vented asymmetrically from the nucleus, rather than simply blown back by solar wind. If 3I-ATLAS is venting asymmetrically, that could explain trajectory anomalies without invoking propulsion systems. It would be entirely natural, but it would also mean the object is more active internally than surface brightness suggests, processing heat and volatiles in ways that aren't fully visible from the outside. The outgassing rates themselves raised eyebrows. For 3I-ATLAS, the observed outgassing rates exceeded model predictions by perhaps 20 to 30%, a significant but not impossible deviation. Higher outgassing could mean the nucleus is smaller and heats more efficiently than size estimates suggest. Or it could indicate ice composition dominated by more volatile species that sublimate more readily than water ice. All natural explanations exist, but higher outgassing combined with unusual chemistry and possible trajectory control starts to build a circumstantial case that something beyond standard cometary behaviour is occurring. Not proof, nowhere near proof, but enough anomalies stacking up that dismissing all of them as coincidence requires increasingly creative natural explanations. Then came the fragmentation hints. In early October 2025, several observation teams reported sudden brightness changes in 3I-ATLAS, brief dips in the light curve lasting hours to days before returning to baseline. Brightness dips can indicate fragment separation, chunks of the nucleus breaking away. Comets fragment regularly, especially during periods of high activity when subsurface ice turns to gas and builds up pressure beneath surface layers. If 3I-ATLAS is shedding fragments, that's completely normal behaviour for a comet under thermal stress. But fragments also mean opportunities. A broken piece spinning away from the main nucleus might reveal internal structure, showing composition or texture that differs from the exterior. If spectroscopy of separated fragments shows different chemistry than the main body, that tells us about internal layering. And if a fragment shows impossibly different chemistry, like metallic composition or molecular patterns inconsistent with natural ices, that tells us we're not looking at a comet at all. The overall chemical picture of 3I-ATLAS remains ambiguous, which is precisely the problem. This one matches most expected patterns, but deviates just enough in specific details to keep uncomfortable questions alive. The carbon dioxide is too strong, the green is too intense, the nickel is too abundant, the outgassing is too high, the tail behaves strangely, fragments might be separating. 2I/Borisov, the last confirmed interstellar comet, looked completely normal in composition. Its ordinariness was reassuring, proof that comets form through similar processes everywhere in the galaxy. 3I-ATLAS is not offering that reassurance. It looks mostly normal, acts mostly normal, but with enough deviations to suggest either rare natural variation or something else entirely. And now it's approaching perihelion, the moment of maximum solar heating, when whatever is happening beneath that dusty surface will accelerate dramatically. If 3I-ATLAS is going to reveal its true nature, perihelion is the moment of truth. But before perihelion arrives, another force is about to test the object's resilience. A coronal mass ejection from the Sun, a billion-ton blob of magnetized plasma, is on a collision course with 3I-ATLAS. The storm is coming, carrying energies that could shatter a comet or activate a dormant machine, depending on what's really out there waiting in the dark. Part 5. Sun-Storm Clash. The sun breathes, and sometimes it screams. On October 4th, 2025, solar observatories detected a major coronal mass ejection erupting from active region 3827, a sprawling cluster of sunspots rotating across the solar disk. The CME launched billions of tons of magnetized plasma into interplanetary space at speeds approaching 2,000 kilometers per second, fast enough to cross the distance from Sun to Earth in about 18 hours. But Earth wasn't in the firing line this time, 3I-ATLAS was. Coronal mass ejections represent some of the most powerful events in the solar system, explosive releases of magnetic energy that can hurl as much mass as a small moon into space at velocities that would vaporize any material object humans have built. When these plasma clouds collide with planets, they compress magnetospheres, trigger auroras, and create geomagnetic storms that can knock out power grids and damage satellites. When they collide with comets, the effects are even more dramatic, because comets don't have protective magnetospheres, just naked nuclei exposed directly to the storm. Astronomers have watched CMEs interact with comets before. In 2007, Comet Encke passed through a particularly strong CME, and solar observatories captured spectacular images of the ion tail being completely disconnected from the nucleus, torn away by magnetic forces and left drifting in space while the comet generated a new tail over the following days. The nucleus survived intact, demonstrating that even direct CME impacts don't necessarily destroy cometary bodies, though they certainly stress them. But 3I-ATLAS isn't a typical comet, or at least the speculation suggests it might not be. If there's any truth to the artifact hypothesis, a CME impact represents a natural experiment in real time. How does the object respond to sudden massive energy input? Does it fragment like a weak rubble pile unable to handle the stress? Does it deflect the plasma like a body with unexpected structural integrity? Does it suddenly brighten, venting stored volatiles in explosive outgassing triggered by the energetic particles? If 3I-ATLAS is purely natural, the CME might trigger fragmentation, breaking the nucleus into pieces that follow diverging trajectories and create a spectacular but ultimately benign display as the fragments gradually separate. This has happened to other comets during moments of high stress. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before impacting Jupiter in 1994. Comet Linear disintegrated completely in 2000, turning from a single nucleus into a cloud of debris in a matter of days. Fragmentation would actually answer many questions. If 3I-ATLAS breaks apart and reveals interior structure inconsistent with natural ice and rock, we'd know immediately that something strange was going on. If it breaks apart and shows exactly the composition expected for a comet, most of the artifact speculation evaporates. Either outcome provides clarity. A CME delivers enormous energy in a sudden pulse, electromagnetic fields and particle bombardment that could serve as both trigger and power source. If you were designing an interstellar probe meant to activate near a star, you might specifically wait for a CME as a sign that solar activity has reached levels capable of supporting operations. The storm becomes a wake-up call, billions of years in transit finally ending at the moment when local conditions say you're home. Ground-based solar telescopes captured images of the CME propagating outward, ghostly coronal structures glowing in extreme ultraviolet light as billion-degree plasma traced magnetic field lines. Space-based instruments like the Solar Dynamics Observatory and the Solar and Heliospheric Observatory provided continuous coverage, tracking the eruption from first emergence through interplanetary expansion. These observations allowed researchers to model the CME's trajectory and predict when and where it would intersect 3I-ATLAS's path. The predicted impact window opened on October 6th at roughly 1400 Universal Time, with uncertainties of plus or minus 6 hours depending on how fast the leading edge of the plasma cloud was actually moving. Observatories worldwide coordinated to provide continuous coverage during this window, imaging 3I-ATLAS at multiple wavelengths to catch any sudden changes in brightness, colour or structure. And then we waited again, for data transmission, for processing, for official analysis to catch up with amateur speculation racing ahead at light speed across social media. Some amateur observers reported seeing brightness changes in 3I-ATLAS during the predicted impact window, sudden surges lasting minutes to hours before fading back to baseline. Others monitoring the same object at the same time saw nothing unusual, suggesting either the changes were below detection threshold for smaller telescopes, or the reports were false positives, seeing patterns in noisy data that weren't really there. Professional observations remain mostly unreleased as of mid-October 2025, still cycling through the usual pipeline of data validation and scientific review. But preliminary statements from some research teams suggested interesting features were captured, a phrase vague enough to mean absolutely anything from spectacular plasma interactions to mildly unusual brightness fluctuations to nothing at all that sounds disappointing in technical jargon. If 3I-ATLAS experienced something truly unusual during the CME impact, something that revealed artificial structure or anomalous behaviour, the data exists somewhere in observational archives. The question is whether it gets released openly or quietly disappears into classified analysis, while public announcements continue emphasising natural explanations. The storm itself has passed by now. The plasma cloud that erupted on October 4th has spread across the inner solar system, washing over Mercury and Venus and Mars and Earth and 3I-ATLAS somewhere along the way. Whatever interaction occurred has already occurred. The electromagnetic pulse already hit, the particles already bombarded, the magnetic fields already clashed and reconnected. If there was going to be activation, or fragmentation, or revelation, it already happened. We're now living in the aftermath, waiting to learn what the aftermath contains. Did the storm reveal a silhouette, exposing structure beneath the cometary disguise as energetic particles stripped away surface layers? Did it trigger dormant systems, jump-starting technology that's been sleeping for millions of years? Or did it simply stress a natural comet in predictable ways, creating a beautiful display of plasma physics that teaches us about solar wind interaction, but nothing about intelligence beyond Earth? The most likely outcome is the boring one. 3I-ATLAS survived the CME with minor fragmentation or surface changes, outgassing rates increased temporarily then stabilized, and life goes on much as before. The storm didn't destroy the comet or activate any hidden mechanisms because there are no hidden mechanisms to activate. Just ice and rock and carbon compounds following the laws of physics through an environment billions of years old. But likely isn't certain, and in the gap between likely and certain lives, every conspiracy theory, every hope and fear about what's really coming toward us from the space between stars. The storm may already be telling us whether 3I-ATLAS is alive or dead, natural or artificial, threat or opportunity. We just don't know which answer we're receiving yet, or whether anyone with access to that answer is planning to share it before the next crisis point arrives. Because perihelion is coming, late October 2025, the moment of closest solar approach, when temperatures peak and thermal stress reaches maximum, and whatever 3I-ATLAS is made of either survives intact or doesn't. The CME was a test, perihelion is the exam, and if there's anything waiting to wake up inside that dusty nucleus, if there's any truth at all to the speculation and rumours and leaked images and unexplained chemistry, then the sun itself is about to provide power levels that make a coronal mass ejection look gentle by comparison. 3I-ATLAS is descending into the furnace, and we're all watching to see what emerges on the other side. Part 6. Origins Beyond Stars. Every object tells a story about where it came from, written in the language of trajectory and composition. For 3I-ATLAS, that story reaches back further than any comet we've studied before, possibly to an epoch when the Milky Way itself was young and our sun hadn't yet formed from collapsing molecular clouds. Trajectory backtracking is a standard technique in orbital mechanics. Take an object's current position and velocity, reverse the equations of motion, and calculate backward through time to determine where it must have been in the past. For objects within the solar system, this technique can reveal encounters with planets, close approaches to the Sun, or origins in specific regions of the asteroid belt or Kuiper belt. The math is straightforward when gravitational forces come primarily from the Sun and maybe Jupiter. For interstellar objects, the backtracking becomes exponentially more complex. You have to account for galactic gravitational fields, perturbations from stellar encounters accumulated over millions of years, even the gravitational influence of molecular clouds and dark matter distributions. The uncertainties compound with time until eventually the error bars become larger than the galaxy itself, and you've lost the trail completely. But researchers are trying anyway, using the most precise trajectory measurements available, and running simulations through galactic dynamics models to see where 3I-ATLAS might have originated. The preliminary results, published in preprint archives and still awaiting peer review, suggest something unexpected. 3I-ATLAS didn't come from the galactic disk, the flat spiral structure where most stars orbit and where our own solar system resides. Its trajectory seems to trace back to the thick disk, a more spherical distribution of older stars orbiting at higher velocities with more random orientations. The thick disk is ancient, populated by stars formed when the galaxy was young, before the distinctive spiral structure fully developed. If 3I-ATLAS originated from the thick disk stellar population, the age implications are staggering. We're potentially looking at material 7 to 8 billion years old, nearly twice the age of our solar system, older than Earth, older than the Sun, formed when the universe was barely half its current age. That makes it the oldest solid object ever studied up close by humans, a time capsule from an era we can usually only observe as distant light from faraway galaxies. But here's the problem. Ice doesn't last 8 billion years. Comets are fragile by cosmic standards, icy bodies that gradually evaporate whenever they approach heat sources or absorb stellar radiation during passage through star systems. Even in interstellar space, supposedly cold and protected, ice slowly sublimates from exposure to cosmic rays and the faint infrared glow of background starlight. Models of cometary survival suggest lifetimes measured in hundreds of millions to perhaps 1 billion years in the interstellar medium, not billions of years. For 3I-ATLAS to still have ice after an 8 billion year journey requires one of several unlikely scenarios. Maybe it spent most of that time deep inside an ultra-cold molecular cloud, shielded from radiation and kept at temperatures close to absolute zero, where sublimation rates drop to near zero. Molecular clouds are enormous, light years across, and an object passing through one could experience millions of years of deep freeze before emerging back into open interstellar space. But molecular clouds don't last billions of years either. They form, spawn stars, and dissipate over timescales of tens of millions of years. For 3I-ATLAS to remain frozen, it would need to somehow pass through multiple successive clouds, threading a path through the densest, coldest regions of the galaxy with remarkable precision. Possible but extremely improbable, like winning the lottery repeatedly over geological time. The alternative explanations veer into speculation. Maybe 3I-ATLAS isn't ancient at all, and the trajectory backtracking is wrong. Orbital reconstruction over billions of years involves so many unknowns and approximations that errors are inevitable. Perhaps the thick disk origin is an artifact of imperfect modelling, and the object actually comes from somewhere much closer and younger that happens to have a trajectory mimicking ancient origins. Or maybe 3I-ATLAS didn't follow a natural trajectory at all. Maybe it was guided. Galactic density waves offer a possible mechanism. The Milky Way's spiral arms aren't fixed structures, but density waves propagating through the galactic disk, regions where star formation triggers temporarily, before the wave pattern rotates onward. These waves perturb stellar orbits, creating ripples that propagate across hundreds of light years and persist for millions of years. Recent data from the Gaia spacecraft, which is mapping stellar positions and velocities with unprecedented precision, has revealed these wave patterns in exquisite detail. Some researchers have proposed that sufficiently advanced civilizations could use these density waves as navigational aids, timing their interstellar launches to catch galactic currents that naturally carry objects between star systems over millions of years. It's cosmic sailing, using the gravitational equivalent of ocean currents to reduce the energy cost of travel. An object launched into the right density wave at the right time could cross vast distances with minimal propulsion, letting galactic dynamics do most of the work. If 3I-ATLAS is riding density waves, its arrival timing wasn't random. It was calculated potentially millions or billions of years ago, to reach this particular region of the galaxy at this particular epoch. The precision required seems impossible, but precision scales with patience. Given enough time to make micro-adjustments, given navigation systems capable of operating over geological timeframes, you could theoretically steer an object across the galaxy using nothing more than well-timed nudges at strategic moments. This crosses firmly into speculation, but it's speculation grounded in real physics. We know density waves exist. We know they affect stellar and interstellar material motions. Using them deliberately for navigation requires technology and planning horizons that dwarf anything humans have achieved, but it doesn't require magic or faster-than-light travel or violations of known physics. The arrival timing adds another layer of coincidence. 3I-ATLAS is approaching our solar system at a moment when human civilization has just barely developed the technology to detect and study interstellar objects. A few decades earlier, we wouldn't have spotted it until after perihelion passage when it would already be leaving. A few decades later assumes we survive long enough to build better detection networks. The current moment represents a brief window of capability and awareness. Is that coincidence? For a naturally occurring object, yes, absolutely. The universe is full of coincidences when you consider how many opportunities there are for them to occur. Throw enough darts randomly, and some will hit bullseyes by pure chance. One interstellar object arriving during humanity's century of astronomical awakening doesn't prove anything beyond the fact that interstellar objects exist and occasionally pass through solar systems. The moment of truth draws closer, and somewhere in the data streams flowing from telescopes around the world, the evidence either exists or doesn't exist to settle whether humanity is truly alone or has been visited by something that was already ancient when our world was young. Part 7. Hidden Propulsion. The search for artificial propulsion in 3I-ATLAS focuses on one key signature: unexplained acceleration, any change in velocity that can't be attributed to gravitational forces or natural outgassing from a comet nucleus under solar heating. Every object moving through the solar system follows predictable paths determined by gravity. The Sun pulls strongest, planets add perturbations, even asteroid belt mass contributes tiny influences to trajectories. With precise enough measurements and powerful enough computers, astronomers can model these gravitational effects and predict where any object should be at any given time with remarkable accuracy. When observations don't match predictions, something is pushing the object in ways gravity alone can't explain. Oumuamua famously showed exactly this kind of anomaly. As it departed the solar system in early 2018, careful tracking revealed it was accelerating away from the Sun faster than gravity could account for. The excess acceleration was small, measured in millionths of a meter per second squared, but it was real and consistent across multiple observation windows from different telescopes. Something was pushing Oumuamua, and the scientific community spent months debating what that something might be. The leading natural explanation involved outgassing, the process where frozen material on a comet's surface absorbs solar heat, turns directly from ice to gas, and vents into space. This venting creates thrust through basic rocket physics. Gas molecules escaping in one direction push the nucleus in the opposite direction. Even tiny outgassing rates can produce measurable acceleration over time, especially for small low-mass objects like Oumuamua. But Oumuamua didn't look like a comet. It showed no visible coma, no dust tail, no obvious signs of active outgassing, despite passing close enough to the Sun that any normal comet would have been blazing with activity. To explain the observed acceleration through outgassing alone required exotic proposals, mostly focusing on hydrogen ice, a substance so volatile and reflective that it would sublimate vigorously without producing visible dust or gas signatures we could detect. The alternative explanation, proposed seriously by a few researchers and less seriously by many more, invoked artificial propulsion. Maybe Oumuamua was a light sail, a thin reflective sheet pushed by solar radiation pressure. Maybe it was a defunct spacecraft tumbling through space, venting propellant or outgassing internal volatiles. Maybe it was an active probe using propulsion systems we don't recognize from external observation. Any of these options would produce unexplained acceleration consistent with what was measured. The scientific consensus settled on natural explanations, because extraordinary claims require extraordinary evidence, and Oumuamua's data, while unusual, wasn't extraordinary enough to justify invoking alien technology. But the debate left open questions and established precedent. If another interstellar object shows similar acceleration anomalies, the artifact hypothesis gains credibility through repetition. Enter 3I-ATLAS, approaching perihelion with trajectory data accumulating daily. Multiple research groups are analysing positional measurements from telescopes worldwide, comparing observed locations against gravitational models to search for deviations. The analysis is ongoing, and results remain preliminary, but whispers suggest something interesting might be emerging from the noise. Some researchers claim the trajectory shows slight adjustments inconsistent with pure gravitational flight, minute velocity changes that appear directional rather than random. These changes are tiny, well within measurement error margins, which means they could be entirely spurious, artifacts of imperfect observations rather than real physical effects, or they could be real, evidence of forces acting on 3I-ATLAS beyond gravity and standard outgassing. The energy cost of even small trajectory adjustments for a massive object is enormous. If 3I-ATLAS really is billions of tons, as recent mass estimates suggest, altering its velocity by even meters per second requires propelling that entire mass against Newton's third law. You need reaction mass, propellant to eject in one direction while the body moves in the other, or you need to push against something external, using solar radiation pressure, magnetic fields, or some other environmental force. Outgassing provides natural propulsion, turning ice into expanding gas that creates thrust. For 3I-ATLAS, the observed outgassing rates could theoretically produce acceleration in the range of what some researchers claim to see in trajectory data. The math works if you assume specific outgassing geometries and efficiencies, but the directionality seems wrong in some analyses, as if the thrust vector doesn't align with where the brightest outgassing activity appears to be concentrated. This misalignment could mean nothing. Cometary nuclei are irregular bodies with complex surface features, and outgassing often occurs from jets on the night side, or from subsurface cavities where you wouldn't see visible coma development. Just because outgassing isn't obvious from Earth-based observations doesn't mean it isn't happening strongly enough to affect trajectory. We could be seeing exactly the acceleration pattern expected from natural processes that happen to be inconveniently oriented for our viewing geometry. Or we could be seeing something else entirely. The search for thruster signatures focuses on emission spectra, looking for ionized exhaust or unusual chemical emissions that don't match typical cometary outgassing. Natural outgassing produces mainly water vapor, carbon dioxide, carbon monoxide, and various organic molecules, all well characterized spectroscopically. If 3I-ATLAS starts emitting xenon ions or metallic plasma, or any of the propellants humans use for electric propulsion systems, that would be immediate evidence of artificial systems. So far, no such signatures have been publicly reported. The emission spectra show carbon dioxide, diatomic carbon, cyanogen, nickel atoms, all consistent with weird but theoretically natural comet chemistry. If there are thrusters operating, they're either using propellants we don't recognize or they're subtle enough that their signatures blend into natural outgassing patterns. Hybrid designs offer a middle ground between purely natural and purely artificial. Imagine a comet nucleus that formed naturally millions or billions of years ago, then got captured and modified by some technological civilization. They keep the icy exterior as radiation shielding and camouflage, but they add internal systems, actuators and control mechanisms that can vent gas directionally to make course corrections. The exterior looks natural, the bulk composition reads as comet, but behaviour deviates subtly from what pure natural processes would produce. This kind of hybrid approach makes sense from an engineering perspective. Building a spacecraft from scratch requires enormous resources and infrastructure. Capturing an existing comet and retrofitting it with minimal control systems uses available materials and provides better protection for sensitive payloads during the interstellar journey. The comet disguise isn't deception, but practical engineering, leveraging natural structures for artificial purposes. Detecting such a hybrid would be nearly impossible from external observation alone. The mass is dominated by natural ice and rock, so density measurements don't reveal small internal components. The outgassing is mostly natural, so spectra look cometary even if small fractions of the gas are being directed deliberately. The trajectory shows acceleration consistent with outgassing, even if the outgassing patterns are being controlled rather than random. You'd need extremely precise measurements across multiple observation windows to catch the telltale signs of deliberate maneuvering. Some analysts claim to see exactly those signs in 3I-ATLAS. Trajectory data, They point to correlations between brightness changes suggesting outgassing events and subsequent velocity changes that seem directionally optimized for trajectory maintenance. The correlations are weak, possibly coincidental, but they're there if you look for them. Statistical significance remains marginal, p-values hovering just above or below the threshold for claiming detection, depending on which analysis methods you trust. The scientific method demands caution with marginal detections. Most anomalies that appear in preliminary data disappear with better measurements and refined analysis. What looks like a signal often turns out to be noise, systematic errors, or artifacts of data processing. Publishing claims of artificial propulsion based on weak statistical evidence invites career damage when subsequent observations fail to confirm the results. But caution cuts both ways. If genuine propulsion signatures exist but remain subtle enough to hide within error margins, waiting for unambiguous proof means potentially missing limited time opportunities to gather more data while the object remains observable. By the time everyone agrees the signal is real, 3I-ATLAS might have passed perihelion and be racing back toward interstellar space, too dim and distant for detailed follow-up observations. This is where post-perihelion tracking becomes critical. If 3I-ATLAS is using propulsion, it will show most clearly after perihelion, when solar heating drops and natural outgassing rates decline. Any continued acceleration in that phase, when thermal forces are decreasing, would be harder to explain through natural means. That's the smoking gun scenario, trajectory changes that persist when they shouldn't, indicating active control rather than passive response to solar heating. The waiting game continues. Perihelion happens in late October 2025, then comes months of post-perihelion observation as 3I-ATLAS recedes from the Sun and heads back toward the outer solar system. If acceleration anomalies appear during that phase, the artifact hypothesis becomes much stronger. If acceleration ceases precisely when outgassing should cease, the natural explanation remains dominant. Part 8. Inside the body. The question of what lies beneath the dusty exterior of 3I-ATLAS leads to some of the most speculative territory in this entire investigation, because we have essentially no direct evidence about internal structure, and won't get any unless the object fragments or permits some kind of penetrating observation. Hollow body hypotheses have circulated since the earlier speculation about Oumuamua's unusual properties. The concept is straightforward. If you're building an interstellar probe designed to carry payloads across galactic distances, you don't make it solid. Solid bodies waste mass on structure that provides no functionality. Instead, you hollow out the interior, creating void spaces that can house equipment, instruments, power systems, or even biological payloads protected by outer shells from radiation and impacts. A hollow body would explain certain observational anomalies, lower average density than solid rock or ice, consistent with mass estimates that seem high for the apparent volume. Unusual structural resilience, surviving thermal and mechanical stresses that should fragment a loosely consolidated rubble pile. Strange acoustic or resonant properties if anyone managed to bounce radar signals off it with enough power to detect internal reflections, though no such observations have been reported publicly. One specific architectural concept that keeps appearing in speculative discussions is the Dyson shard, not a full Dyson sphere but a fragment, a small piece of advanced megastructure technology travelling independently. The original Dyson sphere concept proposed surrounding entire stars with energy-collecting structures, maximising available solar power. Fragments of such structures, launched or broken away and travelling through interstellar space, would be predominantly hollow, thin shells optimised for surface area rather than mass. A Dyson shard crossing the solar system would look strange indeed, too thin and too uniform to be a natural body, probably too reflective unless deliberately coated with dust camouflage. 3I-ATLAS doesn't obviously match that profile, but if you wrapped a shard in accumulated ice and dust from passage through molecular clouds, it might end up looking exactly like a comet, until thermal stress or fragmentation exposed the artificial core. The exotic materials speculation focuses on carbon nanostructures, graphene sheets, Buckminster fullerene molecules, all the wonder materials that human materials science has discovered in laboratories but hasn't yet learned to manufacture at megastructure scales. These materials offer incredible strength-to-weight ratios, thermal properties that help manage extreme temperature swings, and chemical stability that could plausibly survive billions of years if protected from oxidation and mechanical damage. Could such materials survive 8 billion years? Maybe. Carbon structures are chemically stable, and in the cold vacuum of interstellar space, degradation mechanisms are limited mainly to cosmic ray impacts and occasional collisions with interstellar dust grains. With sufficient thickness and redundancy, progressive damage accumulates but doesn't necessarily compromise overall structure. It's like armour that slowly erodes but keeps protecting what's inside until you reach your destination. The thermal stress resistance becomes crucial during perihelion passage. Natural cometary ices crack and fragment when temperature gradients get too extreme. Surface material heated by sunlight while interior remains frozen, creating mechanical stresses that exceed material strength. If 3I-ATLAS survives perihelion intact, despite being subjected to temperatures that should fragment typical comets, that suggest either unusual composition or artificial reinforcement. Hollow structures also provide obvious storage volume for whatever payloads the probe might carry. Instruments package efficiently into designed cavities. Power systems, whether nuclear reactors or exotic alternatives, fit within shielded compartments isolated from external observation. Biological materials, if that's what this mission involves, occupy climate-controlled chambers maintained at stable temperatures regardless of external conditions. The idea of hollow space inside 3I-ATLAS also connects to the module and seed hypotheses that keep recurring in speculative discussions. If the object isn't a single unified structure, but rather a carrier vehicle containing multiple independent packages, those packages need somewhere to sit during the journey. Internal bays, launch tubes, deployment mechanisms, all require volume that solid natural comets don't possess. But here's the challenge with all hollow body speculation. We have no way to confirm it from current observations. Gravity measurements might detect density anomalies if we could put a probe into orbit around 3I-ATLAS, measuring how it gravitationally attracts the orbiter and revealing mass distribution irregularities. But we don't have an orbiter and won't anytime soon. Radar observations might penetrate surface layers and detect internal voids if we had powerful enough transmitters and receivers positioned correctly. But ground-based planetary radar systems have limited range and sensitivity for objects at 3I-ATLAS's current distance. Fragmentation represents the most likely path to internal structure revelation. If perihelion stress causes 3I-ATLAS to break apart, fragments spinning away from the main nucleus might reveal cross-sections showing interior composition. Spectroscopy of fresh surfaces exposed by the break could detect materials not visible in the dusty exterior. Visual imaging might catch glimpses of geometry or structure inconsistent with random fracture patterns in natural ice. Natural explanations for hollow or porous structure do exist. Rubble pile comets, weakly bound aggregations of smaller chunks held together by gravity alone, can have porosity approaching 50%, meaning half the volume is empty space between fragments. This isn't hollow in the sense of designed voids, just loose packing of irregular pieces, but it creates similar average density reductions. Rubble piles form naturally through collisional disruption and gravitational reaccumulation, parent bodies shattered by impacts that don't quite achieve escape velocity, allowing fragments to fall back together into loosely consolidated piles. This process is well documented for solar system asteroids, and likely applies to comets as well. A rubble pile arriving from interstellar space isn't unusual, just a comet that survived its formation environment and happened to get ejected on an escape trajectory. But rubble piles are fragile. They survive through gentle handling, avoiding high accelerations or tidal forces that would pull the pieces apart. 3I-ATLAS is experiencing significant thermal stress during perihelion approach, and survived a CME impact that should have scrambled any loose aggregate. If it remains intact through all that, either it's not a rubble pile, or it has something holding it together beyond mere gravity. The hybrid model combining natural scaffold with artificial shell keeps appearing because it solves multiple problems simultaneously. Start with a natural comet nucleus, providing mass and radiation shielding. Add internal reinforcement, perhaps crystalline structures grown in situ or mechanical supports placed strategically to handle stress. Coat or wrap in artificial materials that protect while maintaining cometary appearance. The result is something that's mostly natural but enhanced in ways that improve survival and functionality. This approach mirrors human engineering philosophy for spacecraft operating in extreme environments. We don't build everything from scratch when natural materials work well. Radiation shielding uses water or polyethylene. materials that occur naturally but get manufactured into useful forms. Structural components use aluminum or titanium, again natural elements processed and shaped. A sufficiently advanced civilization might do similar things at larger scales, using available comet nuclei as raw material and adding minimal artificial structure where needed. The real question about interior structure isn't just whether 3I-ATLAS is hollow or reinforced, or somehow artificial. It's whether that interior serves current purposes or ancient ones. Whether we're looking at an active probe executing a mission, or a derelict artifact that succeeded in crossing the galaxy, but failed to complete whatever it was sent to accomplish. If fragment breaks occur during perihelion passage, if we get lucky and see inside this mysterious object, the interior structure might tell us immediately which scenario applies. Active systems look organized, geometric, intentional. Failed systems look degraded, damaged, non-functional. Natural structure looks random, fractal, geological. The distinction should be obvious if we ever manage to observe it directly. Until then, interior structure remains the perfect hiding place for speculation. Anything could be in there, equipment or biology or empty space or solid ice. And current observations can't distinguish between options. That's simultaneously frustrating for scientists seeking answers, and perfect for those who prefer questions to remain open. We're rapidly approaching the moment when some of those questions might get answered, when thermal stress and solar radiation push 3I-ATLAS to its limits, and either it survives intact or fractures into revealing pieces. The countdown to perihelion continues, days remaining before maximum heating occurs. Whatever secrets hide beneath that dusty exterior, the sun is about to try its best to expose them. And if exposure reveals artificial structure, humanity faces an immediate question that's been theoretical until now. What do we do when we finally have proof we're not alone? Part 9. Conspiracies and Silence. The gap between public disclosure and classified knowledge creates perfect breeding grounds for conspiracy theories, and 3I-ATLAS has generated more than its share during the week since Mars flyby observations allegedly occurred. The viral claim dominating social media focuses on a simple accusation. NASA is deliberately delaying release of Mars observation images because those images show something the public isn't supposed to see yet. The theory proposes that high-resolution photographs from Mars Reconnaissance Orbiter or other assets captured clear evidence of artificial structure during flyby, evidence so unambiguous that standard explanations don't work, and now institutional authorities are deciding how to manage disclosure without triggering mass panic. The shifting explanations offered in official statements, first blaming JPEG artifacts, then pivoting to hot pixels and cosmic rays, look suspicious precisely because they seem like retrofitting rather than confident diagnosis. A genuine compression artifact would be obvious to mission imaging specialists who work with these sensors daily and know exactly what various error sources look like. The fact that explanations keep changing suggests either the analysts aren't confident in their diagnosis, or they're searching for plausible-sounding stories that avoid addressing what they actually see. People misinterpret missing frames regularly in space mission data archives. Not every planned observation succeeds. Tracking failures, pointing errors, timing mistakes, or instrument glitches can result in failed observations that produce no usable data. When those failures occur, the resulting data files might not get uploaded to public archives at all, creating gaps that look suspicious but represent routine operational realities. But transparency matters for building trust. When agencies experience observation failures, announcing them promptly and explaining what went wrong prevents speculation from filling the information vacuum. The silence around Mars observation results fuels suspicion, precisely because it leaves room for imagination. A simple statement like, Mars Express tracking failed due to pointing error, no usable data obtained, would end speculation about that particular dataset immediately. The accusations of gatekeeping and panic prevention rest on historical precedent that's more ambiguous than either supporters or critics acknowledge. Have government agencies classified information about potential extraterrestrial contact? Probably, in the sense that military and intelligence services monitor the skies and classify information about sensor capabilities regardless of what those sensors might detect. The classification protects methods rather than targets, keeping adversaries ignorant about how good our tracking systems are. Has information been suppressed specifically because it related to alien technology? The public evidence for this is thin to non-existent. mostly consisting of testimony from individuals claiming inside knowledge without providing documentation. Every major UFO or UAP incident that's been declassified has turned out to have mundane explanations, sensor artifacts, classified aircraft tests, atmospheric phenomena, or misidentifications of conventional objects under unusual conditions. Secrecy would be expected if probe confirmation occurred, at least initially. The implications of confirmed artificial interstellar object are enormous, touching everything from scientific understanding to philosophical frameworks to geopolitical stability. Responsible disclosure would involve coordination between space agencies, governments, scientific organizations, and probably military and intelligence communities before making public announcements. That coordination takes time, days or weeks minimum for something this significant. The case study of Oumuamua's classified Department of Defense tracking provides illuminating precedent. It emerged months after the object's discovery that military space surveillance systems had monitored Oumuamua continuously, generating high-precision trajectory data superior to anything available from civilian astronomical observations. That data remained classified during the initial public debate about Oumuamua's nature, only being declassified and released after the object had already left the inner solar system. Why classify trajectory data for a natural comet? The official explanation centers on protecting monitoring capabilities, not wanting adversaries to know exactly how precisely US systems can track small objects at interplanetary distances. That explanation makes operational sense from a military perspective. Space debris, satellites, potential weapons, all require precise tracking, and revealing your tracking precision reveals your defensive and offensive capabilities. But the timing of declassification and release after public interest peaked suggests another possibility. Maybe authorities wanted to see how civilian analysis developed before injecting classified data that might redirect investigation. Maybe they were performing their own analysis separately, comparing results against civilian conclusions. Maybe they were simply being cautious with data from sensitive systems, following standard procedures regardless of target. Or maybe they saw something in that high-precision tracking that civilian telescopes missed, something concerning enough to keep quiet while they figured out what it meant. The same pattern could be repeating with 3I-ATLAS. Military space surveillance systems are certainly tracking this object, probably with better precision than civilian observatories achieve. That tracking data is probably classified under the same logic that classified Oumuamua data. And if that classified tracking shows trajectory anomalies more definitively than civilian measurements, we won't know until authorities decide we should know. Suspicion grows when silence fills spaces where information should exist. It's been nearly 2 weeks since Mars flyby occurred. In that time, no official processed images have appeared, no scientific papers submitted to journals, no press releases announcing results. The absence feels conspicuous precisely because this should be a scientifically interesting observation, regardless of whether 3I-ATLAS is natural or artificial. Even routine documentation of an interstellar object's close approach deserves publication. The cynical interpretation suggests data is being sanitized before public upload, interesting frames removed or edited to eliminate anomalous features before the archive goes live. This happens to be technically straightforward with modern image processing tools. Remove a few bright pixels, smooth over geometric patterns, adjust contrast to hide faint structures, and you transform an anomalous image into a mundane one without leaving obvious traces of manipulation. The optimistic interpretation simply accepts that processing complex space science data takes time, and we're still within normal operational timelines. Nothing nefarious is occurring, just scientists being careful and thorough before releasing results that will be scrutinized intensively. The images will appear eventually, probably showing a normal-looking comet with all the alleged anomalies proving to be exactly what official statements claimed, artifacts and noise rather than signal. But optimism requires trust, and trust erodes with every day of unexplained silence. The digital age has conditioned expectations for immediate information access, making even reasonable delays feel suspicious. We're accustomed to instant photo uploads, real-time video streaming, immediate gratification of curiosity through search engines and social media. When space agencies operate on traditional timelines measured in weeks rather than hours, it feels like deliberate obstruction even when it's just normal procedure. The ultimate question underneath all conspiracy theories is simple. If 3I-ATLAS really does show evidence of artificial origin, If NASA or ESA or some military intelligence agency has data proving we're looking at alien technology, would they tell us? And if they decided not to tell us, at least not immediately, would that decision be justified? The arguments for controlled disclosure emphasize preventing panic, maintaining social stability, and allowing time for careful analysis before making civilization-altering announcements. The arguments against secrecy emphasize democratic principles, public right to know, and the impossibility of keeping such secrets in an era of global communication and independent observation. Neither position is obviously wrong. Both reflect legitimate concerns about how humanity handles transformative information, and the tension between them creates the perfect environment for conspiracy theories to thrive, filling knowledge gaps with speculation that can't be definitively disproven until the underlying data becomes public. We're trapped in the gap right now, waiting for data release that either confirms or denies the speculation that's been building since those first leaked images appeared online. The wait could end tomorrow with a flood of processed images showing mundane results. It could stretch for weeks as institutional bureaucracy grinds through review processes. Or it could extend indefinitely if the data really does contain something authorities have decided the public isn't ready to see. The countdown continues, perihelion approaches, and in the absence of official answers, unofficial speculation fills every available communication channel with theories ranging from plausible to absurd, all competing for attention in an information environment where truth and fiction blend into indistinguishable noise. Part 10. Seeds and Swarms. The hypothesis that 3I-ATLAS might be carrying payloads designed for deployment transforms the threat assessment from passive observation to active intervention, a fundamental shift in how seriously we need to take this object's presence in our solar system. Planet seed scenarios start from basic biology and scale up to cosmic engineering. Life on Earth, despite its remarkable diversity, shares common molecular machinery suggesting single origin. DNA uses the same genetic code across all domains. Proteins fold using the same 20 amino acids. Cellular metabolism follows similar pathways. This unity hints that getting life started might be the hard step, while diversification once started becomes inevitable, given time and environmental variation. If life's origin is indeed difficult, requiring precise conditions and unlikely molecular coincidences, then a civilization that figured out how to create or sustain life might see value in spreading it deliberately. Not out of altruism necessarily, but from a kind of cosmic gardening impulse, planting seeds in fertile ground and seeing what grows. An interstellar seed pod would contain genetic material or self-replicating molecular machines, packaged for long-term survival and designed to activate when conditions indicate a suitable environment. 3I-ATLAS approaching a G-type star like our Sun, entering a planetary system showing spectroscopic biosignatures from oxygen-rich atmosphere on the third planet, might interpret these conditions as deployment time. The seed payload activates, perhaps using perihelion heat as power source, and begins whatever release mechanism was designed billions of years ago by entities long extinct or evolved beyond recognition. The delivery system could be as simple as cometary fragmentation. Thermal stress at perihelion cracks the nucleus, embedded seed packages separate from the main body, and each fragment follows slightly different trajectory determined by outgassing thrust and initial separation velocity. Some fragments impact planets, some enter stable orbits, some escape the solar system entirely. It's shotgun dispersal, low precision but robust, requiring no sophisticated guidance, just careful initial design. Or delivery could be targeted, using propulsion systems to steer fragments towards specific destinations after separation. Mars received attention during the October flyby, possibly as reconnaissance to determine suitability for seeding. Earth comes into range in weeks or months, depending on orbital phasing. The Moon, Venus, even asteroids or moons of Jupiter might receive payloads if the mission profile involves comprehensive solar system seeding rather than focusing on single targets. What would seeds contain? The optimistic version involves simple organic molecules, amino acids and nucleotides and lipids, the chemical building blocks necessary for life, but not life itself. These molecules delivered to sterile worlds might catalyze the origin of indigenous life, jump-starting biological evolution that otherwise takes billions of years to begin from scratch. It's panspermia on purpose, directed rather than random, intelligent design, without requiring ongoing divine intervention. The moderate version delivers complete self-replicating systems, synthetic cells or protein machines capable of reproduction and evolution. These wouldn't be intelligent, just molecular machinery following programmed instruction sets, but they'd be alive by most reasonable definitions. Released into suitable environments, they'd multiply, diversify, and eventually evolve into complexity that might reach intelligence given enough time. The seeding civilization doesn't control the outcome, just initiates the process and lets natural selection drive development. Earth already has biology, which complicates any seed scenario. Introducing new organisms to an established ecosystem creates competition, predation, and potential collapse if the newcomers lack natural checks on their expansion. Invasive species on Earth demonstrate how devastating successful invaders can be to native biodiversity. An invasive species from another star system, evolved under completely different selection pressures and possibly using different biochemistry, could be catastrophically disruptive. Or it could be completely ineffective, unable to function in Earth's chemical environment, killed immediately by oxidative stress or temperature shock, or any of the thousands of conditions that Earth-adapted life takes for granted. Interstellar biology faces an enormous challenge, needing to survive both the journey and deployment into environments that might be fundamentally incompatible with its operating requirements. The multi-phase invasion model escalates threat levels dramatically by proposing not seeds, but invasion forces, organised deployment of technological or biological systems designed to establish control over encountered planetary systems. In this scenario, 3I-ATLAS isn't a single entity but a mothership, a carrier vessel transporting multiple modules that separate during perihelion passage and pursue independent missions. Phase 1 involves reconnaissance, surveying the solar system to identify resources, threats, and targets of interest. The Mars flyby serves this purpose, close approach allowing detailed observation of planetary conditions, atmospheric composition, surface features, and possibly detection of technological signatures indicating intelligent inhabitants. If Mars showed civilization, different modules might deploy than if it appeared sterile. Phase 2 activates based on reconnaissance results. Modules separate from the main body, each carrying specific payloads tailored for different objectives. Some might target resource-rich asteroids, establishing mining and manufacturing infrastructure using self-replicating machines. Others might head for outer system moons, setting up bases in radiation-shielded subsurface oceans. Still others might aim for Earth, either to make contact with detected civilization or to neutralize potential threats before establishing dominance. Phase 3 involves consolidation and expansion, modules coordinating to build infrastructure supporting longer-term presence. Communication networks establish, allowing separated units to share information and coordinate actions. Manufacturing ramps up, using local materials to construct additional modules beyond what the mothership originally carried. Population grows, whether biological organisms reproducing or machines self-replicating, until the invading force reaches sufficient numbers to accomplish whatever mission objectives were programmed. This scenario sounds like science fiction, because it is science fiction, speculative military analysis, applied to interstellar context, with minimal connection to actual observations of 3I-ATLAS. But it's worth considering precisely because the consequences of being wrong about dismissing such scenarios are catastrophic. If there's even a small probability that 3I-ATLAS represents coordinated invasion, rather than passive natural object, the appropriate response differs fundamentally from scientific observation protocols. Biological payload scenarios raise different but equally troubling concerns. If 3I-ATLAS is carrying life, whether simple molecules or complex organisms, any contamination of Earth's biosphere could have irreversible consequences. Quarantine protocols exist for returned Mars samples, procedures designed to contain unknown biology until safety testing confirms no threat. But those protocols assume controlled return missions with material arriving in sealed containers, not cometary fragments burning through atmosphere and scattering debris across continents. If 3I-ATLAS carries genuinely alien biochemistry, using different genetic codes or alternative molecular machinery or exotic solvents instead of water, contamination might be self-limiting. The alien biology simply can't function in Earth conditions, dies immediately upon exposure, and poses no ongoing threat. This is the optimistic scenario where biochemical incompatibility protects both biospheres from mutual disruption. The real threat may not be 3I-ATLAS itself, massive and conspicuous and trackable by every major telescope. The real threat is what it carries and releases, smaller objects that scatter into the darkness and pursue individual missions while we focus on the mothership. By the time we realise distribution occurred, the dispersed elements might already be established beyond our capability to locate or neutralise. This is worst-case thinking, catastrophic scenario planning that responsible defence establishments conduct regardless of actual probability. The likelihood remains overwhelmingly high that 3I-ATLAS is just a comet, the Mars streak was just artifact, and no invasion or seeding is occurring. But the consequences of being wrong are so severe that even tiny probabilities deserve serious consideration and preparation. Perihelion is days away. If module deployment happens, it happens soon. And if nothing happens, if 3I-ATLAS passes perihelion and continues outbound showing no signs of fragment release or anomalous behaviour, the speculation gradually fades and we return to normal operations until the next interstellar visitor arrives, and the whole cycle repeats. But this time feels different. The accumulation of anomalies, the timing of observations, the institutional silence, all combine to suggest something more than routine science is unfolding. Maybe it's all coincidence and misinterpretation. Or maybe we're watching the opening moves of an encounter that will define human civilization's future more profoundly than any event in recorded history. The clock is ticking. The modules might already be launched, and we have no idea what comes next. Part 11. Galactic Waves and Pathfinding. The Milky Way isn't static. It's a dynamic system of flowing matter and energy, where invisible currents can carry objects across interstellar distances just as ocean currents carry ships across earthly seas. Recent data from the Gaia spacecraft has revealed these currents in unprecedented detail, and they raise intriguing possibilities about how 3I-ATLAS arrived at our doorstep. Gaia has measured over 1 billion stars with precision that reveals not just where stars are but how they're moving. When those measurements get assembled into galactic maps, patterns emerge. Stars don't orbit the galactic centre in perfect circles. They show wave-like perturbations, ripples in the fabric of the galaxy itself propagating across thousands of light years. These density waves represent regions where matter accumulates temporarily before the wave pattern rotates onward, like traffic jams that persist even as individual cars move through them. Star formation concentrates in density waves, where gas clouds compress to critical densities. Spiral arms trace these waves, marking where stars and nebulae cluster more densely than average. But density waves don't just affect stars and gas. They perturb everything in their path, including dark comets drifting through interstellar space. An object crossing through a density wave experiences enhanced gravitational forces that slightly alter its trajectory. Over millions of years and multiple wave crossings, these perturbations accumulate into significant course changes, steering objects in predictable directions even without any propulsion. Think of it as gravitational surfing. Launch an object with initial velocity that intersects upcoming density waves at optimal angles, and those waves naturally guide the trajectory toward your target. The steering is gentle but persistent, requiring no fuel expenditure, just patience and precision in timing the initial launch. For interstellar voyages measured in millions of years, this approach makes enormous sense, letting galactic dynamics do the heavy lifting while onboard systems conserve energy. Could 3I-ATLAS be riding these waves? Trajectory reconstruction suggests possible alignment with known density wave patterns, though uncertainties remain large. If the object originated from the thick disk population as some models suggest, it might have encountered multiple waves during its journey, each encounter slightly redirecting its path until accumulating adjustments aimed it toward our solar system. The implications are profound. If advanced civilizations understand galactic dynamics well enough to use density waves as navigation aids, then interstellar travel becomes more feasible. You don't need enormous energy budgets to accelerate payloads to relativistic speeds, just enough propulsion to reach appropriate wave-catching trajectories and then wait while the galaxy itself carries your probe to its destination. This fits the idea of timed arrival windows. Density waves rotate with predictable periods, creating lanes of enhanced steering that appear and disappear on regular cycles. 3I-ATLAS arriving now, during the early 21st century when human civilization has just developed detection capabilities, could represent such a timed window. Not coincidence, but calculation. a trajectory planned to intersect our solar system at an epoch determined by galactic orbital mechanics, millions or billions of years ago. The parallel to Polynesian navigation is more than metaphor. Pacific islanders crossed thousands of miles of open ocean, without instruments, using wave patterns and subtle environmental cues to find tiny islands in vast emptiness. They worked with the ocean, reading currents to guide their canoes efficiently. Galactic navigation could operate on similar principles at incomprehensibly larger scales, reading density waves to steer between star systems. If wave riding is real, it raises questions about agency versus accident. Is 3I-ATLAS arrival the result of deliberate navigation using understood galactic dynamics? Or is it accidental trajectory that happened to align with waves by pure chance? The distinction matters enormously. Deliberate arrival implies intelligence and planning, even if the planners are long dead. Accidental arrival implies nothing beyond random motion through a structured environment. Current observations can't distinguish between options. Unless 3I-ATLAS shows obvious course corrections during its approach, the navigation question remains open. But if wave riding is possible, if density waves really do provide exploitable structure for efficient interstellar travel, then the universe becomes more connected than we'd assumed. Not empty void crossed only by lucky accident, but a network of pathways linking star systems together through patterns that persist across galactic time. Civilizations using these pathways could seed probes throughout the galaxy, not through brute force propulsion, but through patient exploitation of natural dynamics. This suggests the galaxy may already be seeded with probes following wave patterns, thousands or millions of objects crossing between systems on trajectories calculated to maximize coverage while minimizing energy expenditure. Most pass unnoticed through uninhabited systems. Occasionally one arrives where someone is watching, and we get cases like Oumuamua and 3I-ATLAS, brief glimpses of the traffic constantly flowing through galactic space. Our location in the galaxy is unremarkable, about halfway out from centre in the Orion Arm, a minor spur between major spiral arms. Nothing about our position seems special from a navigation perspective, unless the unspecial position is exactly the point. Major star-forming regions in spiral arms are chaotic, dense with supernova and disruptive radiation. Quieter interarm regions like where we reside might be preferred because they're stable, offering better survival odds for fragile biological worlds. A seeding campaign targeting life-bearing planets might focus on these quieter neighbourhoods. The universe itself becomes a seeded garden under this framework. Density waves carrying biological or technological packages between systems, distributing the products of successful civilizations across the galaxy over billions of years. Earth life might be one result of such seeding, though proving or disproving panspermia origin remains essentially impossible without finding clear evidence of artificial design in our genetics. If 3I-ATLAS is part of this distribution network, if it's riding waves and carrying seeds, then its arrival doesn't represent special attention to Earth specifically. We just happen to be along its route, one destination among potentially thousands. This is simultaneously comforting and unsettling. Comforting because it suggests no targeted threat. Unsettling because it means we're not special, just another potentially fertile location in an ancient seeding operation we never consented to participate in. The existence of galactic-scale navigation also answers timing questions. If wave routes determine timing rather than intelligence signals, then arrival epoch is fixed by orbital mechanics rather than synchronized with civilization maturity. 3I-ATLAS arrives now because the waves brought it now, not because anyone was monitoring Earth. But that assumes no local adjustments. If the probe has been dormant during most of its journey, but activates as it approaches solar systems, it might make final trajectory tweaks to ensure approach geometry optimized for its mission. Mars flyby could represent such an adjustment, using gravitational assist or small propulsive maneuvers to target Earth more precisely than the wave route alone provided. We're watching cosmic navigation in real time if any of this speculation proves accurate. 3I-ATLAS riding galactic currents toward a destination chosen billions of years ago, now executing final approach maneuvers while humans scramble to understand what we're seeing. This is no longer a question of whether we're alone. If wave-riding probes exist, if the galaxy contains navigation networks connecting star systems through exploitable dynamics, then intelligence has been spreading through space for eons. We're late arrivals to a party that's been running since the universe was young, finally developing the technology to notice that we're not the first guests to show up. Whether the other guests are friendly, indifferent, or hostile remains the critical unknown. The same waves that carry seeds of life could carry weapons or surveillance systems, or simply scientific instruments. Until 3I-ATLAS reveals more about its nature and purpose, we're left inferring from patterns and possibilities. Perihelion approaches, bringing revelation or disappointment depending on what the universe decides to show us. The waves continue their eternal rotation, indifferent to whether anyone notices the pathways they create through the darkness between stars. Part 12. Enceladus Organics Boom. While attention focuses on 3I-ATLAS and its mysteries, another discovery from September 2025 quietly reshapes our understanding of where life might exist and what that means for interstellar seeding scenarios. Saturn's moon Enceladus, long known to harbour a subsurface ocean, has yielded spectroscopic evidence of complex organic molecules far more sophisticated than previously detected. The discovery came from analysis of plume material ejected from Enceladus's south polar geysers, ice particles containing ocean water that escaped the moon's weak gravity and spread through Saturn's E-ring. The Cassini mission extensively sampled these plumes during multiple flybys between 2004 and 2017, detecting simple organic molecules, salts, and evidence for hydrothermal activity on the ocean floor. New analysis using updated spectroscopic techniques and better calibration has revealed amino acid precursors in archived Cassini data, complex carbon-nitrogen compounds that represent building blocks for proteins. These aren't amino acids themselves, but molecules one or two chemical steps away, suggesting that Enceladus ocean chemistry creates conditions where biochemically relevant synthesis occurs naturally. This confirms what astrobiologists have suspected, that ocean worlds throughout the solar system and presumably throughout the galaxy provide environments where life's chemical prerequisites emerge spontaneously. Europa orbiting Jupiter, Titan orbiting Saturn, Ganymede and Callisto and possibly several other moons all likely contain subsurface oceans where similar chemistry might occur. Ocean worlds outnumber rocky planets with surface water, making them potentially the most common habitable environment in the universe. If life emerges easily in ocean worlds, and ocean worlds are common, then life itself becomes common by extension. Not intelligent life necessarily, since the path from simple chemistry to complex cognition requires additional unlikely steps, but at least microbial life or its equivalent. The universe fills with biology, most of it hidden beneath icy crusts, invisible to surface telescopes, waiting to be discovered by any civilization advanced enough to drill through kilometers of ice or sample ejected plumes. This expands the plausibility of life-seeding probes dramatically. If you're a civilization that's discovered how to create or accelerate the origin of life, and you're looking for places to plant seeds, ocean worlds become prime targets. They're common, they're stable, they provide liquid water and chemical energy, and they're protected from surface radiation that might damage fragile early life forms. Dropping biological packages into ocean worlds through impacts or deliberate penetration makes strategic sense for maximizing successful seeding events. Earth stops being unique in this framework, just one example among billions of potential habitats scattered throughout the galaxy. 3I-ATLAS arriving in a solar system containing multiple ocean worlds might target those moons rather than focusing exclusively on Earth. Mars got attention during flyby possibly because its past as an ocean world still shows in geological record. Europa becomes high-interest target. Enceladus itself might receive a payload if 3I-ATLAS trajectory allows close Saturn encounter. Enceladus serves as test case for how seeding could work practically. The moon's plumes already demonstrate that interior ocean material reaches space naturally, no drilling required. A probe arriving in the Saturn system could simply release biological packages into the plume regions, letting natural ejection carry the material into orbit where some fraction rains back down onto the surface. Over thousands of years, Some packages work their way through ice fractures into the ocean below, arriving in the habitable environment without requiring the probe to land or penetrate ice itself. This highlights how alien seeding strategies might work differently from human assumptions. We imagined spacecraft landing on planets, deploying robotic landers, drilling cores, very direct hands-on approaches. But a civilization operating on million-year timescales might prefer passive strategies, releasing packages in positions where natural processes eventually deliver them to target locations. Patience removes the need for sophisticated landing systems, letting gravity and geology do the work. If Enceladus Ocean contains actual life, discovered during future missions designed to sample and analyze plume material more thoroughly, the question becomes whether that life originated independently or was seeded. Independent origin on both Earth and Enceladus would strongly suggest life emerges easily, reinforcing the idea that the galaxy teems with biology. Seeded origin, possibly detected through genetic analysis showing similarities too precise for convergent evolution, would prove that transfer between ocean worlds occurs either naturally or artificially. Earth's place in this biological cosmos shifts from unique jewel to ordinary participant. We're not the only life, possibly not even the first life in our own solar system, if Enceladus life predates Earth's origin. The psychological impact of this realization operates on multiple levels, simultaneously diminishing human significance while expanding the scope of what biology represents across cosmic scales. 3I-ATLAS carrying seeds becomes less shocking in a universe where ocean worlds harbour abundant potential habitats. Instead of asking whether seeding happens, the question becomes how extensively it's been practiced and whether Earth participated. Did our planet receive visitors carrying biological packages that jump-started or influenced terrestrial evolution? Current data can't answer, but improving understanding of early Earth conditions and better biochemical analysis might eventually reveal signatures of external input. This connects back to 3I-ATLAS age and origins. An 8-billion-year-old probe from the thick disk might have been launched by one of the galaxy's first civilizations, entities that arose when the universe was barely half its current age, and achieved technology while most star systems still lacked rocky planets. They couldn't visit Earth because Earth didn't exist yet. But they could send packages, designed to activate when encountering suitable systems billions of years in the future, preserving their biology across timescales that saw the rise and fall of countless subsequent civilizations. We might be descendants of the galaxy's first intelligence, children of seeders so ancient that their original biology has evolved beyond recognition through billions of years of selection in diverse environments. Earth life could be one branch on a family tree that spans the Milky Way, related to organisms in ocean worlds throughout the galaxy through common artificial ancestry. Or Earth life could be completely independent, having emerged purely through terrestrial chemistry, without any external input. The universe is large enough for both seeded and independent origins to occur simultaneously, making any particular world's biology ambiguous in isolation. Only by finding life elsewhere and comparing it to terrestrial biology can we determine which scenario applies to us. The boom in Enceladus organic detections doesn't prove seeding happens. It proves ocean worlds are more interesting biologically than we'd assumed, raising the stakes for exploration and the plausibility of finding life elsewhere. Whether that life originated locally or through delivery from external sources remains open question, requiring data we don't yet possess. But the timing is suggestive. Enceladus results announced in September, 3I-ATLAS approaching perihelion in October. Both events occurring simultaneously creates narrative connection, even if physically unrelated. We're discovering our solar system contains more potential for life precisely as an interstellar object, possibly carrying life approaches closest solar distance. Coincidence or convergence? Random timing or somehow synchronized in ways we don't understand yet? Perihelion comes soon, bringing answers or new questions depending on what 3I-ATLAS reveals. And Enceladus waits beneath Saturn's rings, plumes still erupting, oceans still churning, possibly harbouring biology that's been there longer than humans have existed, waiting for us to develop technology capable of finding it. The solar system is busier than we thought, more alive with possibilities and connections, less sterile isolation, and more cosmic intersection. Whether we like it or not, we're participants in processes larger than planetary or even stellar scales, caught up in galactic dynamics that were ancient before our world formed. The only question is whether we're just observers of these processes or about to become active participants in whatever happens next. Part 13. Comet Swan 2025 R2. The cosmic coincidences keep accumulating. In late September 2025, amateur astronomer Hiroshi Takahashi, using the solar wind anisotropies instrument, remotely accessible through citizen science programs, discovered another comet inbound to the inner solar system, designated C 2025 R2 Swan, following standard nomenclature. Initial observations suggested typical long-period comet from the Oort cloud, nothing immediately unusual beyond the fact that any new comet generates interest among astronomical communities. But as observatories worldwide began tracking Swan R2, strange features emerged that echo some of 3I-ATLAS's more mysterious characteristics. The comet is developing faster than models predicted. Brightness increased more rapidly than typical for objects at its distance from the Sun, suggesting either underestimated nucleus size or unusually active outgassing. By early October, Swan R2 was visible in amateur telescopes, showing distinct green coloration reminiscent of 3I-ATLAS's unusual glow. Green comets aren't rare, as discussed earlier. Diatomic carbon produces that colour commonly. But two comets showing strong green signatures simultaneously in the same time period crosses from normal into statistically improbable. Not impossible. Comet chemistry depends on composition, which clusters in formation regions, so multiple comets from similar origins might share unusual colours. Still, the parallel invites comparison. Swan R2's trajectory places it on a path that could intersect meteor shower material from previous cometary debris streams, creating opportunities for Earth-based observation of fragment interactions. Some predictions suggest Swan R2's tail might pass through regions where Taurid or Geminid meteors concentrate, potentially creating visible interactions as fresh cometary material mingles with older debris. The spectroscopic signatures from Swan R2 show carbon dioxide dominance similar to 3I-ATLAS, though less extreme. Water vapour is present but subdued, giving the coma composition that doesn't perfectly match typical long-period comet expectations. Again, not impossible naturally, just unusual enough to note. What makes Swan R2 particularly interesting for conspiracy-minded observers is the timing. Two unusual comets approaching the inner solar system simultaneously, both showing atypical chemistry, both displaying similar green coloration, arriving within weeks of each other. This coincidence triggers speculation about coordinated arrivals, multiple probes entering the solar system together as part of organised campaign. The scientific community points out that the Oort cloud constantly sheds comets toward the Sun, with several dozen new discoveries typical in any given year. Most are faint and unremarkable. Occasionally multiple bright comets appear in close succession, purely through random clustering. The solar system has experienced far more impressive cometary shows in historical times, like the 1996 to 1997 period when both comets Hyakutake and Hale-Bopp were visible to the naked eye weeks apart. But Swan R2 isn't just another Oort cloud comet in the same year as 3I-ATLAS. It's another unusually behaving comet with chemical oddities appearing during the exact month when 3I-ATLAS approaches perihelion. The overlap in timing creates narrative connections that persist, even when scientific analysis says coincidence is the correct explanation. Speculators claim this represents swarm arrival, multiple interstellar objects entering the solar system together like a fleet rather than isolated traveller. In this scenario, 3I-ATLAS is just one element of coordinated presence, with Swan R2 potentially being another probe, or even a natural comet being herded by artificial shepherding systems. The entire inner solar system is experiencing elevated visitation, because something is happening, some galactic event or intelligence decision that scheduled multiple arrivals for this specific time frame. Scientists counter that Swan R2's trajectory traces clearly back to the Oort cloud, rather than interstellar origins, making it definitely a solar system native. Unless, conspiracy theories respond, the trajectory reconstruction is wrong, or the object spent time in the Oort cloud after arriving from interstellar space, making its immediate origin local while its ultimate origin remains external. You can't definitively prove an object hasn't been captured and inserted into solar system orbits, if that capture occurred millions of years ago beyond observational horizons. The parallel between SWAN R2's glow and 3I-ATLAS's glow triggers speculation about shared chemistry or engineering. If both objects are probes using similar propulsion, or surface coatings or emission signatures, they might naturally look similar from external observation despite being physically separate entities. Standardization across probe designs makes sense from engineering perspective, using proven technologies repeatedly rather than customizing each mission individually. Or green glow means nothing beyond carbon chemistry, and we're seeing patterns in coincidental similarities, the same pattern matching that makes us see faces in clouds or find conspiracies in unrelated events. The human mind excels at finding connections, often too well, detecting correlations where only randomness exists. What would confirm swarm hypothesis? Detection of additional objects showing similar anomalies, too many for coincidence to explain. Clear communication or coordination between separate objects, trajectory changes that suggest mutual awareness and planning. Discovery of additional fragments or modules separated from either 3I-ATLAS or SWAN R2, showing artificial structure or capabilities, none of which has occurred yet, leaving speculation in the realm of possibility rather than evidence. The question lingers though, why these two comets now? Statistical clustering happens, random events bunch together by chance. But is that the complete explanation? If we saw 3 or 4 or 5 unusual comets arriving in the same month, would that finally exceed the threshold of coincidence and force acknowledgement that something coordinated is occurring? How many anomalies does it take before the natural explanation becomes less probable than the artificial one? We're not there yet with SWAN R2 and 3I-ATLAS, still within the realm where conventional astronomy handles observations without invoking alien probes. But we're closer than we've been before, closer to the edge where the extraordinary evidence matches the extraordinary claim. SWAN R2 continues approaching, brightening as solar heating increases, developing its tail and coma according to physical laws that govern cometary behaviour. Observations continue, spectra accumulate, trajectory refines. Eventually we'll know whether this comet remains scientifically ordinary, despite superficial similarities to 3I-ATLAS, or whether it develops its own set of anomalies requiring explanation. The cliffhanger question drives engagement. Are multiple anomalies random or not? Human psychology craves patterns and meanings, struggles with accepting that sometimes randomness produces apparently significant correlations. 2 green comets arriving together could be pure chance, or could be signal that we're in the middle of something larger than we've recognised yet. Perihelion for 3I-ATLAS arrives in days. SWAN R2 follows weeks later. If both objects behave normally during closest solar approach, showing standard cometary evolution with no anomalies beyond initial chemical oddities, then the natural explanation wins and speculation fades. If either shows dramatic unexpected behaviour, fragmentation revealing structure or trajectory changes or module deployment, then every other anomaly gets re-examined in light of confirmation that something artificial is present. We wait and watch, telescopes pointed skyward, collecting photons that travelled millions of kilometres to reach our sensors, trying to decode what those photons tell us about the nature of reality and whether we're still alone in experiencing it. Part 14. Near-miss asteroids. The sky isn't just home to distant comets and interstellar visitors, it's also full of rocks, thousands of near-Earth asteroids crossing orbits that sometimes bring them uncomfortably close to our planet. On October 10th, 2025, one of these rocks, designated 2025 TF, missed Earth by roughly 100,000 kilometres, closer than the orbit of the Moon, and well within the sphere where satellites operate. 2025 TF wasn't detected until October 9th, roughly 36 hours before closest approach. This isn't unusual for smaller asteroids, objects in the 10 to 30 metre size range, that don't reflect much sunlight and approach from directions where solar glare makes detection difficult. The asteroid passed harmlessly, providing another data point about how many objects we're not seeing until they're essentially already here. This detection gap becomes terrifying when applied to 3I-ATLAS fragment scenarios. If a 10-metre asteroid can evade detection until hours before closest approach, How many smaller fragments could 3I-ATLAS release without us noticing? Objects in the 1 to 5 metre range would be essentially invisible until they entered the atmosphere or impacted something, too small and dark to show up in current survey telescopes. The planetary defence community has made enormous progress in cataloguing larger potentially hazardous asteroids, objects above 140 metres diameter that could cause regional devastation. Current surveys have found more than 90% of these large near-Earth asteroids, giving decades of warning for anything big enough to threaten cities. But smaller objects remain largely untracked. The number of 10-metre asteroids crossing Earth's orbit is estimated in the millions, with only a tiny fraction catalogued. These objects wouldn't cause global catastrophe if they impacted, but they could destroy neighbourhoods, create tsunami if they hit oceans, or generate regional effects. And we're essentially blind to most of them until they're already arriving. This is where sleeper probe hypothesis becomes strategically concerning. If 3I-ATLAS released small modules during Mars flyby, or earlier in its approach, those modules could be following independent trajectories toward Earth, or other targets right now, invisible to current detection systems, waiting to arrive on timelines we can't predict, because we don't know they exist. The modules wouldn't need to be large to accomplish various mission objectives. A 10-metre object contains hundreds of tons of material, more than enough for sophisticated payloads if the engineering is sufficiently advanced. Communications equipment, sensors, even self-replication systems could fit within volumes we'd struggle to detect until they're already operational. Earth orbit itself could already host such objects without our knowledge. Geosynchronous orbit at 36,000 kilometers altitude contains thousands of active satellites, but surveillance of that region remains incomplete. Objects deliberately designed for stealth, minimizing reflectivity and emissions, could hide among the debris and satellites that already clutter that orbital shell. The phrase, "what if one's already in orbit?" triggers maximum paranoia because it's genuinely difficult to rule out. Space surveillance networks track objects large enough and reflective enough to see, but detection thresholds leave gaps. An object the size of a car or shipping container, coated in radar-absorbing material, and positioned in crowded orbital regions, might escape notice for extended periods. The sleeper probe concept suggests dormancy followed by activation when specific triggers occur, so an object might sit inert for months or years showing no signatures, before suddenly powering up and executing programmed instructions. Detection after activation becomes easier since active systems generate electromagnetic emissions, but activation might also mean the mission is already succeeding. This paranoia isn't baseless fear-mongering, it's realistic assessment of what's possible given detection limits and potential adversary capabilities. If we're dealing with technology from civilizations millions or billions of years more advanced, assuming they can hide small objects in near-Earth space is conservative thinking. The policy gap becomes obvious. Planetary defense infrastructure focuses on natural threats, asteroids and comets, following ballistic trajectories predictable through gravitational models. These systems aren't designed for intelligent threats that maneuver deliberately, coordinate actions, or employ countermeasures against detection and tracking. If 3I-ATLAS represents artificial system deploying modules, the existing infrastructure is poorly matched to the threat profile. Detecting deployment events requires continuous observation with sensors that can catch brief, high-acceleration burns or fragment separation. Tracking deployed modules requires persistent surveillance of volumes too large for current assets to cover continuously. We're not prepared for this scenario, not because anyone was negligent, but because preparing for every possible low-probability, high-consequence threat exceeds available resources. But maybe that calculation needs updating if observations continue accumulating evidence that we're experiencing unusual visitation. The cost of being wrong about dismissing artificial origin for 3I-ATLAS could be catastrophic if modules are deploying and we're ignoring it. Risk assessment should favour caution when asymmetry is this extreme. We should be watching 3I-ATLAS more intensively, dedicating more telescope time, treating this as potential first contact rather than routine astronomy. Even if probability remains low, the magnitude of potential consequences justifies elevated response. Whether such elevated response is actually occurring behind classified doors remains unknown to public observers. Space Force maintains satellites with capabilities not publicly disclosed. If they're concerned about 3I-ATLAS, we wouldn't necessarily know. The connection back to Mars streak observations completes the circle of concern. If that streak was a module, if 3I-ATLAS deployed something during Mars flyby, then the operational phase already began. More modules might have deployed since, invisible against background stars spreading through the inner solar system toward various targets. We might be surrounded by probes right now, instruments watching us, systems preparing for activation, and we're completely unaware because our detection capabilities weren't designed to catch such things. 2025 TF served as a reminder that space isn't empty, that objects cross near Earth constantly, that detection isn't guaranteed until impacts occur. If those objects become intelligent and numerous, if swarms deploy from motherships arriving disguised as comets, current defences provide almost no protection. Time is running out to improve those defences if they're needed. Perihelion happens in days. Module deployment, if it occurs, happens at perihelion when energy availability peaks and target positions optimise. We're living through the window of maximum threat, the days when deployment is most likely if it's going to happen at all, and we're mostly just watching, telescopes pointed upward, collecting data, analysing images, waiting to see what the universe shows us. Active defence requires recognising threat and accepting that extraordinary measures are justified. We're not there yet, still in the analysis phase where scientific caution dominates over security urgency. Maybe that's the right approach. Maybe 3I-ATLAS is just a comet, and all these fears are unfounded paranoia driven by too much imagination and too little evidence. But maybe we're about to learn that caution becomes catastrophic when it prevents preparation for threats that turn out to be real. The asteroids keep coming, detected late if at all, reminding us that the sky holds dangers we don't see until they're already here. Whether those dangers are rocks or probes, natural or artificial, might not matter much if we're equally unprepared for both. Part 15. Final Countdown. We've reached the end of this investigation, at least the end of what can be said before perihelion forces nature to reveal its hand. The moment arrives in days, the point where 3I-ATLAS passes closest to the Sun and experiences maximum thermal stress, maximum energy input, maximum opportunity for whatever revelation or disappointment awaits. Let's review the scorecard. The mass estimates suggesting billions of tons could be natural, but push the limits of what typical comets contain. The trajectory stability during interstellar journey requires unlikely environmental history. The Mars flyby imaging anomalies could be compression artifacts, but official explanations kept shifting. The unusual chemistry with excess carbon dioxide and nickel falls outside standard distributions. The green glow appears unusually intense. The CME impact survival suggests structural resilience beyond typical rubble piles. The possible trajectory adjustments show geometry wrong for natural venting. The 8 billion year age implies impossibly long ice survival. The timing of arrival during human detection capability feels suspicious. None of these anomalies individually proves artificial origin. All have natural explanations that work if you accept various unlikely but possible conditions. But the cumulative weight of multiple anomalies occurring simultaneously creates a pattern that becomes harder to dismiss. At some point, the natural explanation requiring 12 unlikely coincidences becomes less probable than the artificial explanation requiring one that 3I-ATLAS is a probe. We're not at that point yet for most scientists. The conservative assessment says interesting object worthy of detailed study, but no compelling evidence for artificial origin. The speculative assessment says too many red flags to ignore. Both positions are defensible given available data. 3 timelines bracket the possible futures. The hours to days timeline applies if something dramatic occurs during perihelion passage, immediate fragmentation revealing internal structure, sudden trajectory changes indicating propulsion activation, module deployment visible in real time, or communication signals transmitted using solar power. If any of that happens, humanity knows within hours that we're dealing with artifact. The weeks to months timeline applies if changes occur more subtly. Post-perihelion trajectory analysis, taking time to confirm anomalies, fragment spectroscopy revealing unusual composition, or deployed modules becoming detectable as they disperse. This timeline allows scientific verification before public disclosure, institutional deliberation about how to present findings. The year-plus timeline applies if nothing obvious happens, 3I-ATLAS passing perihelion and heading outbound showing behaviour consistent with natural comet, speculation gradually fading as new observations fail to support artifact hypothesis. This includes the possibility of delayed activation, probes waiting months or years after perihelion before executing mission operations. Each timeline ties to specific triggers. Perihelion itself on October 28th 2025, when solar heating peaks and thermal stress maximizes. Tail disruption or fragment release would be visible within days. Post-perihelion acceleration anomalies would become apparent within weeks as trajectory measurements accumulate. The emphasis on living through the countdown right now is crucial. This isn't historical analysis of past events. This is present tense unfolding situation where every day brings new observations and potential revelations. Right now, today, telescopes are tracking 3I-ATLAS. Right now, instruments are collecting spectra and images. Right now, something real is happening in the space between Mars and the Sun, and we're watching it happen. The worst-case scenario involves module swarm deployment at perihelion, dozens or hundreds of objects separating from main nucleus and heading toward various targets throughout the inner solar system. The swarm disperses quickly, individual modules too small and dark to track consistently, disappearing into the solar system's vastness, while executing programming determined millions or billions of years ago. The middle case puts 3I-ATLAS as a spectacular comet, providing scientific bonanza without existential threat. Unusual chemistry teaches us about interstellar formation environments. Fragment releases allow direct spectroscopy of interior composition. Nothing fundamentally changes about human civilization except we learn more about how comets work. This is probably the most likely outcome based on prior experience with Oumuamua and Borisov, both of which generated speculation but ultimately proved more ordinary than extraordinary. The best case depends on perspective. From a pure science standpoint, the best case is an active probe willing to communicate, providing direct information about its origin, builders, and mission. First contact with alien intelligence, even if that intelligence is millions of years dead. The knowledge gained would revolutionize every field from physics to philosophy. From a security standpoint, the best case is a natural comet confirmed definitively through observations leaving no room for speculation. Threat eliminated, paranoia diffused, resources redirected toward actual challenges. The viewer takeaway emphasizes that surveillance never ends. 3I-ATLAS isn't the last interstellar object we'll encounter. Survey telescopes are improving, detection capabilities expanding, and future visitors will arrive with increasing frequency. Each new arrival triggers similar cycles of speculation and analysis, gradually building a dataset that either confirms these objects are natural or accumulates enough anomalies to prove artificial presence. We're participants in something ancient, whether that something is natural physics operating across billions of years or intelligence reaching across the galaxy to touch our world. The scale overwhelms comprehension, but the reality is immediate. Right now, in our sky, an object that travelled from incomprehensible distances is passing through our neighbourhood, and we're capable of watching it happen. That alone represents remarkable human achievement regardless of what 3I-ATLAS ultimately proves to be. A century ago, we barely understood that other galaxies existed. 50 years ago, we'd never detected an interstellar object. Today, we track them, analyse their composition, debate their nature, and seriously consider whether they might represent alien technology. The last line delivers the hook. If the rumours are true, how long do we have? The clock is already ticking. It's present tense, immediate stakes, forcing recognition that resolution comes soon, not someday in the abstract future, but now, this month, while you're living your normal life unaware that cosmic dice are rolling. Maybe we have all the time in the world because 3I-ATLAS is just a comet, and no threat exists. Maybe we have months or years before deployed modules reach operational capability. Maybe we have zero time, modules already positioned and waiting only for activation signals. The uncertainty is the point. We don't know. Despite all our telescopes and analysis and speculation, we genuinely don't know what 3I-ATLAS is or what happens next. The universe is about to tell us, ready or not. Perihelion arrives. October 28th, 2025. The waiting ends. The truth, whatever it is, begins revealing itself in sunlight and shadow, in trajectories and spectra, in presence or absence of the signals we've been watching for. The clock is ticking. How long do we have? Days until perihelion. Weeks until post-perihelion analysis completes. Months until scientific consensus emerges. Years until the next interstellar visitor arrives and the cycle repeats. Or maybe we have no time at all, and everything changes before you look up at the night sky. before anyone realizes that the rumors were true, and the countdown ended while we were still trying to decide whether to take it seriously. The object is out there, moving, changing, approaching its moment of truth. And we're here, watching, waiting, wondering whether this is the story that future generations will remember as the moment everything changed, or just another footnote in the long history of cosmic visitors that came and went, leaving nothing behind but data and fading speculation. The answer arrives soon. The universe is about to speak. Whether anyone is ready to hear what it says, that's a different question entirely.